Hi everyone, my name is Jeroen Eyckmans. I'm a research professor here at BU in the biomedical engineering campus. My lab is actually right upstairs here. And so my team is really interested in how do cells repair tissues after injury. And injury is something that affects us all. Through lifestyle, every organism gets injured and needs to be repaired. And as we age, that process slows down, and in many cases, actually, it stops. And so you end up with these open wounds or aberrant scarring. And so this is just an example, just to guide you a little bit through what the process involves. This is the knee of yours truly after an unsolicited bike fall end of last year. Right after injury, what happens, you get bleeding, and then it stops, fortunately. That's what we call hemostasis. You get through the first stages involve inflammation, clearing out dead matrix. Then we get new cells coming in like fibroblasts. They rebuild sort of that pinkish tissue, which we call granulation tissue. Also, if you see the folds in my skin there, it's indicative of contractility, contraction. So this is why a lot of wounds actually hurt 48 hours after injury, because the surrounding tissue is contracting in order to speed up wound healing. And then that new granulation tissue basically is required for epithelial cells, which is the top layer of your skin, to move in and seal the wound again and restore the barrier function, right? So my lab is really interested in understanding more of that granulation tissue formation, because that is, cells are producing extracellular matrix. And as we age, that extracellular matrix may actually change and may affect how we heal. So how do we do that? We built these organ-on-chip models. In this case, this is a wound-on-a-chip model where we have fibroblasts embedded in a collagen matrix. They're put in these microwells with standing pillars. So you can create these microtissues, and then with a laser, we actually create these wounds, and then the cells are able to heal that, right? So there is no surface there. They really heal it through assembly of a matrix. This is what you see on the right here. So in cyan is fibronectin, which is a matrix molecule also dominantly present during wound healing. So that is how the model system works. So if we, for example, do this with different types of cells, in this case we have neonatal fibroblasts, we see an initial opening of the wound, that means the wound is cleared, and then a rapid decline, which is it heals fast. Older or adult neonatal cells, the adult fibroblasts, they actually take more time to heal. So in this context, we were looking at senescent cells. As we age, we have an accumulating number of damaged cells that go into senescent state. And so we were wondering if senescent cells actually show also delayed wound healing. And indeed, it sort of phenocopies the young versus adult cell types here. So here we have neonatal cells, they heal rapid, whereas when we induce senescence in those cells, we get sort of a slowed down healing profile. So then we were wondering, well, as everyone is looking sort of at the cell type itself, we were interested whether these cells produce different types of ECM and whether that ECM affects already wound healing. So we did this experiment where we have these neonatal cells, and the control condition is actually the lower graph there. That's the fast healing one, so that is in rat tail collagen. But then we changed the extracellular matrix to what normal cells would produce, which is the middle line. Or when we have senescent fibroblasts producing their matrix and we mix it in the model system, we actually see a larger opening and delayed wound healing. So the senescent ECM clearly affects wound healing in this case, and here is the same experiment we've done with senescent fibroblasts. So the moment you have that senescent matrix in there, you actually don't get any closure at all. Now, most of the effect is seen in the opening or in the clearance of the wound healing. So we're looking here at the maximum opening of the wound, and when we overexpress collagen type 1, in this case, in senescent fibroblasts, we actually see that we can get a reduction from the maximum opening back to basically normal, which makes us think that if we can modulate the ECM, we can start developing therapies to make us more resilient to injury as we age. So with this, I leave it to the next person.